Welcome to Superheroes of Science. I'm Stephen.
And I'm Sarah. We co-host Science from the Experts. Our guests are professionals doing cutting-edge science right now.
They're experts in their field discussing what they know best. So listen up and learn real science from real people.
Subscribe now and stay informed of our latest episodes and show your support. Today on Superheroes of Science, we are here with Assistant Professor Dan Dawson here in the Department of Earth, Atmospheric and Planetary Sciences at Purdue University. So welcome. Thanks for joining us today.
Thanks for having me. I'm looking forward to it.
And I want to say you're like Dan the Tornado Man. Is that fair? Can I say that?
we have three different professors named Dan in the department, and so there's been this, how are we going to distinguish them? So I'm supposedly Tornado Dan, and we also have Cloud Dan and Hurricane Dan. And
Okay. Yeah.
I work with clouds too, but it just tornado works better.
But you're the one faculty that I've talked to at least. I'm guessing Robin's done some chasing, but it seems to be the whole storm chasing's kind of been something that you do.
Oh yeah, do it a lot.
And so that's your thing. I know we've talked before about how you've spent and took off for the day because there was a storm coming through to see where it was going to be, trying to follow it up and or intersect, I should say.
Right.
Okay.
So yeah, it depends on the scenario, but like we do, well, both of us do storm chasing both for research and for just for amateur. We do it for as a hobby as well as research, and also trying to report things to the Weather Service.
Okay.
And impromptu spotting of, like, for example, if there's a storm nearby, I'll have to go up to the roof. By the way, you gotta be careful with these things, lightning danger or whatever, but just to look and get an idea what the storm's doing, and relay that to the Weather Service if possible. Or we'll go out storm chasing. I don't know how much you wanted to talk about this. We have a class devoted to learning about severe storms and how to chase them effectively, how to deploy instrumentation around them, and basically do a real field project. So it's a mixture of all of those things, sort of hobby, research, and for public service.
Mm-hmm.
And sometimes they merge together, and it's not always easy to break those apart, but yeah.
So the only thing I had a problem with what you said is when you started to say amateur. So I don't think you can call yourself an amateur at anything in this field.
Depends on what you call it. So amateur, it's interesting because different people have different ideas of what that means. So when I say amateur, I don't mean like less sophisticated. Okay, I mean doing it not as part of your job, like something that you're interested in doing. For example, an amateur astronomer. Amateur astronomers, I'm an amateur astronomer. I have a telescope. I use it occasionally when I can, take astrophotography, but I'm not a professional astronomer. I don't do it as my job.
Okay.
But I could, lots of amateur astronomers make some really high quality and important observations.
Yeah.
So it's not like they're a second tier. Okay. Mm-hmm. Same thing when it comes to amateur storm chasing. I'm both an amateur and a professional.
Okay.
In that regard.
Right.
Does that make sense?
Yes.
That's how I look.
For some reason it does.
Yeah.
So now by professional, I mean I do the storm chasing as part of my research, like this recent field program we did, not as there are other professional storm chasers that's actually what they do, their job. They actually make a livelihood by just going and chasing storms, getting video. Nothing wrong with that. That's not me. I don't do. It's part of my professional.
Because you're a research scientist, correct?
Yes. Yeah.
Correct.
Yeah.
And is your main research, is it the tornadoes or just the types of storms? What is your narrowed down focus?
So the short answer is yes. I study storms and tornadoes. So I'm interested in all aspects of severe thunderstorms, how they form, what the mechanisms surrounding how they produce their severe weather. So that can include high winds, hail, and tornadoes. My emphasis is on understanding processes related to development of tornadoes and the storms. But I also focus on other aspects of the storms that don't necessarily have a direct connection to the tornadoes too. So I do a little bit of all of that.
Okay.
Yeah, that's sort of my sort of corpus of research around storm and tornado dynamics. behavior. Yeah.
I know a lot of people that there's a lot of fear, right, surrounding just even the idea of tornadoes, that people are just like, oh my goodness, I don't know. So surrounding, you said the parts that maybe form the tornado, right, the process of a tornado formation. What does that look like? Or is it too varied, or are there some definite components that
No, that's, it's a good question. I'll try to break that apart in a couple different ways. One is tornadoes can form in many different types of thunderstorms.
Okay.
The most common type, the type of storms, so storms come in different flavors, different species, so to speak. The kind of species of thunderstorm that produces tornadoes most frequently and the most intense are called supercell storms.
Okay.
And a supercell storm is simply a storm, in the most simplest definition you can come up with, is a storm that has a rotating updraft. So all thunderstorms have updrafts in them. That is air that's rising very rapidly in the center of the storm. As that air is rising, it's cooling off, water vapor in the air is condensing onto cloud droplets. So that's where the cloud comes from, the deep, and it's doing that. As it's doing that, it's releasing heat to the air. It's heating up the air, making the air more buoyant, which accelerates the updraft. So that's the fuel force for pretty much any thunderstorm, is that heat coming from the condensation of water vapor onto the cloud drops as the air is expanding and cooling off. And so every storm has an updraft, and often several of them, kind of, depending on the type of storm. You have what's called a single cell storm, which a cell being in storm parlance means an updraft and downdraft together, coupled.
Okay.
So you can think of a storm cell as being somewhat analogous to a biological cell, in that it's like the fundamental unit of a convective storm is this cell, which is an updraft and downdraft together. Just like every person has multiple cells, and that's their fundamental life unit is a cell, right?
Yeah.
It's kind of like that. So a lot of storms, you can have single cell storms. You can also have multi-cell storms. Those are the most common, where there's several cells kind of in different stages of their life cycle acting together as a single unit. And the supercell is a more organized form where it's back to a single cell, but it's a large updraft and it's rotating. And so that's the fundamental definition, is a storm that has a deep, persistent, rotating updraft.
Okay.
And these supercells often have distinct features when you look at them on radar. They have this region of very heavy precipitation and then this region of lighter precipitation that sort of spreads out ahead of it. It's called the forward flank of the storm. And on the backside of the storm, there's often a hook echo, which is sort of like this streamer of precipitation that wraps around in a sort of counterclockwise fashion, cyclonic fashion around where the circulation is, where the rotating updraft is. Now, a tornado, if it's going to form, will tend to form very close to the base of that updraft, near the edge of where that updraft and the downdraft of the storm is located.
Okay.
It tends to form right at that edge near the tip of the hook echo. That's for a supercell. Other types of storms, like squall lines, storms that form along a line, which lots of people are probably familiar with, can also produce tornadoes. They tend to be produced in embedded circulations within that line. Sometimes you'll even have supercells embedded in the line.
Oh, wow.
And tornadoes can form in those. But they can also form in these shallow little small spin-ups along the line. And those are hard to predict and detect ahead of time. Tornadoes that form in squall lines tend to be, on average, weaker and not as long-lived as those that form from supercells, but they still can be dangerous. Just got done with a field program that is specifically designed to study tornadoes from linear storms. We've studied a lot of the supercell type. We still have a lot to learn about that, don't get me wrong, but much less so have we studied the ones that form in lines, because historically they've been less deadly, less of a direct threat, so to speak, on the hierarchy. But we're changing that now. We're starting to study those more. So but yes, I think I kind of went off a little bit on a tangent there. But to get back to your question, tornadoes, so obviously not all thunderstorms produce tornadoes. Not even all supercells produce tornadoes. In fact, some estimates that less than 10 to 20% of them do.
Okay.
But they all have rotation in the storms itself.
Yeah, a supercell is defined by that. It has to have a rotating updraft.
Right, but not necessarily a tornado.
Correct. Yes, and there's a good reason for that. The scale of the rotation of a supercell's updraft, it tends to be pretty large, around 10 kilometers or so in diameter, and they're not very vigorous rotation relative to that of a tornado. Tornado is a very concentrated, very rapidly rotating vortex. A mesocyclone is a larger, broader, more weakly rotating vortex, and it also tends to be higher up in the storm, above the ground. So not necessarily connected directly to the ground.
Okay.
So in order to get from that to a tornado, lots of things have to happen that depend on many different processes in the atmosphere that we're still learning about. It turns out that we know that a supercell is more likely to produce a tornado if certain things in the environment are primed for it. So one big example is if we have a lot of wind shear in the lowest kilometer or so above the ground. So that means an increase of wind speed with height and change in direction with height. All supercells need that over a big deep layer, somewhere between the surface to 6 kilometers above the ground, where you have that wind shear, and that helps produce the rotation. Now I could go all day about this, but we probably don't have all day. But the idea is that if you have this wind shear, the wind increases with height and speed with height and changes direction, that sets up a sense of rotation around a horizontal axis. So if you think about it this way, if you think about having like a rolling pin, you're rolling it along, and you put this giant rolling pin with the axis laying out on the ground, and the top of the rolling pin is at 6 kilometers above ground and the bottom's near the ground. Or even think of it as this giant paddle wheel, if that helps, like a water wheel or something like that. It's probably better. You know, if the wind's blowing faster at the top of it than it is at the bottom, you're going to start the thing rotating around that horizontal axis, right?
Okay.
So there's this sense, it's not that there actually is this rotation around a horizontal axis, it's that there's this propensity for that from the wind shear.
Okay.
What happens when a storm comes along is this updraft kind of pokes into that, and it takes that rotation around the horizontal axis and tilts it upward. Kind of bends the whole tube, so to speak. I'm simplifying it a little bit, but the idea is that you get that isolated tilting, and then other processes go along to kind of concentrate and stretch that, and that's where you get the rotation of the updraft for a supercell. So you need wind shear environment. You need a certain amount. So supercells like that kind of wind shear. They also like instability in the atmosphere, so that's where the temperature is dropping off fast enough with height in the environment, like as measured, say, by a weather balloon that's rising up, so that the air parcels that are rising up in the updraft of the storm are that much more warmer than their surroundings. The warmer they are relative to their surroundings, and they're warm again, remember, by that heat released by the condensation. So they end up being a lot warmer than the environment, and if the environment is cooling off fast enough, that makes it even warmer. That makes it less dense relative to its environment. So that increases the buoyant force upward. It's accelerating upward. Just like if I took a beach ball and shoved it under the water. You know, everybody's done this, right? It really wants to move up.
Yeah.
Right? The bigger the beach ball, the more it wants to move up because it's buoyant. It's less dense than the surrounding water. The water wants to push it up. Same thing is happening in a storm. The air parcels inside the storm are less dense than those surrounding it. So if you look at a big storm in the sky, you think, wow, that looks like it's heavy with water and it's all, you know, like this. It's actually less massive, less dense overall, in the updraft at least, than the air surrounding it that is dry and cloud-free. It's kind of counterintuitive, but it's less dense, at least in the updraft, not in the downdraft part, but the updraft, because of all that heat that's being released, making the air less dense.
Okay.
So that's all this. That is what creates the updraft. The more that instability is, the more that temperature drops off in the environment with height and some other things. The more moisture there is in the atmosphere, the more humidity there is in the low levels to fuel it. That means there's more condensation, more heating. So that increases the intensity. It's called the convective available potential energy. We can actually calculate this.
Okay.
We send a weather balloon up. We know what the temperature and the dew point are doing as they go up. We can calculate this thing called CAPE, which tells you a sort of an upper bound of how intense that updraft is going to be.
Oh.
Okay. So those two together and that wind shear generate that initial rotation of the updraft. Now, a tornado, though, needs more than that. It needs, we've seen that environments that have a lot of that wind shear just in the lowest few hundred meters above ground tend to favor tornadoes more than others, because that creates a stronger rotation of the mesocyclone closer to the ground. You get more like a vacuum effect near the ground. It's like wants to draw the air up into it. It also, the lower the base of the cloud, the lower it is when the air that's rising up first becomes saturated and produces cloud. That's also favorable for tornadoes. There's a lot of other things that go into this. So just because you have the environment favorable for a supercell doesn't necessarily mean it's favorable for a tornado. You need some additional tweaks in the environment, so to speak. And so that's the basics of these processes. And we can tell a lot by just looking at, say, the environment that we get from a weather balloon. But the processes that actually go into developing the tornado and the storm are extremely complicated. So we can have all the potential there, but if something else is wrong, the way the storm is behaving, maybe the storm is merging with other storms and that's interfering with its life cycle, or maybe the outflow of the storm is too cold. We have too much cool air coming out of it. Even if everything else looks favorable, we may not get a tornado. And the other way is true as well. Sometimes the environment, just from looking at the environment ahead of the storm, doesn't look particularly favorable, but other things are happening that tip the scales to maybe create a tornado that may not have been there. And these are the things that I study, is the dynamics, the physics of how individual storms are behaving. So.
Oh, very cool. But now when we have a tornado, and it starts off with that funnel cloud, it always comes, does it actually start from the clouds and come down? Because it perceives to. So is that actually how that rotation is happening?
So that's a really, really good question. And there's, I can spend a lot of time on it, but I'm going to very briefly say that the short answer to your question is that tornadoes form from the bottom up. However, there's some things to keep to understand why there's this idea that they form from the top down. There's two reasons historically that has been a theory. One is that in earlier days of studying tornadoes, when still today, the best tools we have are for studying storms on this time and space scales that are important for this kind of thing are radars. Okay, and the weather radars can scan, but they can't scan really close to the ground because the beam would hit trees and other obstacles. So we have to tilt the beam up a little bit. So unless you're really close to the radar, you're typically scanning more than a couple hundred meters or more above the ground is the lowest you can get. And so we can only detect the rotation in a storm above the ground. We can't detect it near the surface with the radar, okay? Unless, again, with special circumstances like mobile radars on trucks that we can get right up close and personal. But in general, we can't do that. And so what we'll often see is that the storm's mesocyclone will intensify, and then a tornado will form. So that led to this sort of idea, this is cause and effect, that the rotation starts in the middle part of the storm and then descends later, okay? But as we've come to learn over the years, that is way too simple of a picture. It is true that often the mesocyclone intensifies before a tornado forms. But what's going on is that as it's intensifying that vacuum sucking effect. You're getting that intensification of the updraft. The actual rotation that goes into developing the tornado forms at the surface underneath that from other processes which we're still learning. How do we get that vertical rotation right near the ground? That is the holy grail of tornado research, is to figure out exactly how that happens. And there's still lots of theories and what we're working on that. But assuming you can get this region of rotation near the surface, now you need something to concentrate that. You know, the proverbial skater on the ice, conservation of angular momentum, pulling it in. That's part of it. It's not the whole story. But that's particularly for the beginning phase of the tornado, where you've got this broader rotation, you're trying to tighten it up. You need something to do that. And the way to do that is if you're stretching air. We're sucking air up, like think of a vacuum cleaner hose over the ground and you're pulling air up into it, then that's also causing air to rush in from the sides, right? For conservation of mass. If there's rotation in that air, it's also going to tighten that rotation. Okay? And so we think that the final stage of tornadogenesis, just before you get a tornado when you didn't have one before, at least is from that final stretching, concentration and stretching of that rotation. And that's a bottom-up process. It starts from the ground up. But the actual sucking that's going on, the stretching of the air into and acceleration of the updraft, is happening in part because of the intensification of the rotation above it. So the rotation in the mesocyclone is indirectly related to the rotation of the tornado in that it helps concentrate it down below by the virtue of its updraft. Does that make sense? It's kind of complicated.
Yeah.
And then without a way to gather that data, it's just difficult to try to piece those.
Exactly, right. So we can't see all that's happening unless we have special instrumentation nearby, and that's why we have these field programs to try to put as much instrumentation around. We also use numerical simulations to try to get at that, but we need to know our numerical simulations. We don't know, they're very complicated, and we are treating a lot of the processes that are going on in a simplified manner. So we need to be able to validate what we're seeing in the simulations with what we're actually observing. So we need everything. We need the field programs to get data collected near the ground in close proximity, and we need the simulations to help understand the processes going on, because even the best field program, we're not going to get data everywhere we need it. The simulation can fill in those gaps, but they have to feed off of each other. But yes, that's the idea, is that I said the short answer was it's a bottom up. The longer answer is it's a little bit of both. It's complicated. Yeah.
Now the ones that don't, if it's just a funnel cloud and it doesn't touch the ground, is that also starting bottom up, or is that one dipping down?
So yeah, I'm glad you mentioned that, because that's the second reason why there's often this idea out there that tornadoes come from the cloud down, is that that's what it looks like a lot of times.
Yeah.
When you're watching a video of a tornado that's forming a funnel cloud, you'll often see that the funnel will start extending down toward the ground. And then you think, oh, so the tornado's coming out of the cloud. No, that's not what's happening. It's an optical illusion. Nothing is moving down, okay? What is moving down, it's like, one analogy I use, if you take a pair of scissors, I wish I could show you, but you take a pair of scissors, and you start with them open and then you close it, you can look at the intersection point of the scissors, right?
Yeah.
And as you close the scissors, you see that intersection point moving along it. But is anything actually moving that direction? No, it's just that point of intersection.
Yeah.
The blades are actually moving horizontally in that case. So in a tornado that's forming, the air is coming in near the ground and moving up, okay? Now, as the tornado develops, you can also get a downdraft in the center of the tornado, but that's not relevant to this discussion. But in general, the air is coming in the base and moving up. The funnel cloud is moving down only because what's happening is that as the air's concentrating, the rotation spinning up, as you start increasing the rotation, the pressure drops. Those two go hand in hand. Rotating air is associated with low pressure in the center. Okay. And as the rotation intensifies, the pressure gets lower. Well, the lower the pressure, the more the air is expanding as it goes up, the more it's cooling off, and it starts condensing cloud at a lower altitude than before. So what you're seeing is cloud forming at lower and lower altitudes as the air is rushing up. But the air is always going up the whole time. It's just the point where the cloud is forming that you can see it is moving down towards the ground. But that is not a physical object, it's just a location where this process is happening. Just like that, the scissor, the two blades coming together, it's just a point where that, does that make sense?
It does.
It does.
Yeah,
so it's a total optical illusion. There's no actual object like air that's moving down with that cloud. It's just the clouds forming at lower and lower altitudes. Which also helps explain the other point here, is that a tornado is not the funnel cloud. A tornado is the air. It's the wind. Okay, it's the vortex. By itself, if there wasn't any cloud in the area, it could be invisible unless it was picking up debris and dirt and stuff.
Uh-huh.
And in fact, in many cases, you can have a tornado in progress where the funnel cloud is maybe even not even present or only partway reaching the ground. So don't just rely, if you see a funnel cloud in the distance and you don't see it touching the ground, it's not mean there's not a tornado there. In fact, often there is. One way to tell, again, this is I'm going to say this wrong. It's a necessary but not sufficient condition that you have the strong no, I'm going to say that wrong. The idea is that if you see a funnel cloud in the distance, and if you see like dirt and debris swirling around at the base of it, that is sufficient for it to be a tornado. Sufficient condition. Because what you have is strong enough winds rotating around near the ground to actually start doing some damage. Okay. That's the basic idea that when you have a tornado. If you have a funnel cloud, but there's not a strong surface circulation, which can happen yet, then that's not a tornado. But it's often very difficult to tell that from a distance.
Right.
So you can't assume just because you don't see the funnel cloud reaching the ground that there's not a tornado there. The tornado is just the wind. Now as the tornado intensifies, the rotation intensifies, generally you'll see that funnel start to move down toward the ground, but it doesn't always make it all the way. So there are many cases with tornadoes where what you'll see is sort of like the funnel cloud in the middle tapering down, but then you'll see this column of dirt and debris that's kind of sheathing it around it. That's a tornado. Just because the funnel cloud is not all the way to the ground doesn't mean it's not a tornado. I know it sounds like a broken record, but that's very important to understand this. And depending on the environment, if you have for example, you have an environment that's relatively dry, like sometimes this can happen out in the plains, western plains, high plains, where there's just not as much moisture around. And you can have cases where you have storms with pretty high cloud bases, and you'll get tornadoes that often won't have any visible funnel cloud. You'll see rotation at the base of the cloud, and you'll see the debris swirling around and dust rising up, but that's all it will be a dust tube. A tube of dust without hardly any cloud in it. And that's still a tornado, even if there's no funnel cloud at all. So, yeah. But in general, often, typically, as a tornado gets going, you will eventually get a funnel cloud that reaches the surface. So just the whole point of me what I'm saying there is that that's not a necessary condition for that, for a tornado. It's like an accessory. It's an attendant to what's actually going on. That's important.
Well, that is cool.
That is really cool.
See, I've heard like bits and pieces, so I didn't really know for sure, to be honest. So that's what I asked for me.
No. It's a great question. I get a lot. And if you ever take spotter training with the Weather Service, they'll go over this too. It's one of the key things because when they want people to report tornadoes, they want them to understand what it is they're looking at, and that what even if it's just a funnel cloud doesn't mean that there's not a tornado there. Now what they'll do is we have these rules of thumb for spotting purposes. Okay. That if we're out there and we're a certain distance from a tornado, and we see the funnel cloud and it's only a quarter of the way from the cloud base to the ground, oftentimes we say it's probably not a tornado there. Again, though, it can be. The rule of thumb that we often use, but again, it's just a rule of thumb and it's very variable from case to case, is that if the funnel reaches about halfway to the surface, there's probably, very likely, a surface circulation that's tornadic. Okay. So then what we'll say, okay, there's probably a tornado here and call it in or whatever. So, yeah.
Fair enough. That's cool.
That is cool.
Thank you for listening to this episode of Science from the Experts from Purdue University's Superheroes of Science.
If you like this episode, subscribe, give us a positive review, and share the love. Boiler up!
Hammer down.